Welcome. My name is Samantha Flynn. Here I am on Muddy Math for all of you. We're talking about ratios today. Those of you currently in my class, you do have an assignment online called Ratios Grade 6. What kind and how many? It's an illustrative mathematics task. I love this task. It brings in geometry and some friendly imagery for us to use and sort of collect data, ask questions, and use ratios to make sense of what's going on. Here you'll see directions for students working in my class currently to help you through the assignment. I will post a link to the Google Slides in Google Classroom and a link to the Illustrative Mathematics website that this entire video is derived from. So big thanks to Illustrative Mathematics for setting us up with this wonderful task, and we will get started. I'm going to make a copy of this because I want to make sure I am only working on a demonstration slide. And I have my iPhone recording as well because I'm afraid that the whiteboard's not going to show up really well on the Screencastify. So for that reason, I'm going to minimize myself here. I will post both videos. I could edit them and bring them together, but I don't feel like it. So mathematics concept that we're working on is ratios. You see that a ratio is the quotient of two numbers. So quotient gives us division. When we think about division, we can use fraction bars. We also have, of course, our old school division symbol, which of course has a beautiful name that is escaping me right now. The quotient of the two numbers forms the ratio. When you have a quotient, that means division. Quotient is technically the solution to a division problem. So if you're thinking about a ratio, it's always helpful to try to interpret the final value. If you were to actually divide those two numbers, what would that be saying? Does it make sense? Does it not make sense? Are these things that should be compared? Can we divide them? Is it a part to a whole or a part to a part? We'll get into all that soon. A ratio can be written in the form A over B, like a fraction, but it doesn't always follow the same properties as fractions, and we'll talk more about that in the future. For example, you can write a ratio using a fraction, but fraction and ratio are not just equivalent words, is what I'm saying there. You can use a colon. We see the two dots in the line, the line, A to B, the two dots in the line. It's a common symbol that we'll see with ratios, division, fractions, and such. It can be written as an ordered pair, which is super important moving forward, and I feel like this is a little bit that I see missed a lot, not conceptually, but explicitly. It's really important that we say very specifically, and I love this book written by Bendick Levin and Simon McGraw-Hill, old school McGraw-Hill book. Evidence that I do like textbooks. I love textbooks, actually. Behind this whiteboard is a ton of textbooks. So what year is this from? Let's see. This is from 1965. Awesome. But this book is just full of definitions and pictures, and that's what I love about it because it helps us frame what we're talking about. So this definition is super important, and I'm going to jump back to the Screencastify and read the definition here. It says a ratio is an association between two or more quantities. So let's compare that to the definition we have here, the quotient of two numbers. An association between two or more quantities. You can definitions, there are many ways to define something, right? So what makes more sense to you? Thinking about a ratio as two numbers related by division. So the quotient of two numbers is essentially two numbers related by division, creating a third value that represents the two number comparison. Or we can think about Screencastify. A ratio is an association, and let me clear screen and go into slideshow mode because that would make the most sense. A ratio is an association between two or more quantities. So these are different words, but over here I have stars and circles, and in Screencastify we have blue squares and green squares. 3 to 2, and fancy that 2 to 3. I have the exact same example here as you see in the illustrative mathematics definition and example, but it's just different symbols. What is important to know is that, let me see. This is a side note, and this is why a lot of you get kind of exhausted with me, but that's okay. McGraw-Hill Education is the author, or not the author, but the publisher of illustrative mathematics these days. And boom, McGraw-Hill Mathematics Illustrative Dictionary. So this world of mathematics is very close, and you are welcome to join it and bring in your piece of mathematics. Anyway, I digress. Clear rectangle, clear screen, back, and here. Okay. So, an example you see on the cover page of the illustrative mathematics, the glossary entry, which I believe comes at the end of the illustrative mathematics, but I think it should come first. We see the example, the ratio of 3 to 2. Here you might see 3 rows of 3 and 2 rows of 3. Okay, so we have the ratio of 3 to 2. This is the ratio of 3 to 2. But in the United States, we read from left to right, and in other parts of the world, we read from left to right. So we might read this as 2 to 3. But the cool thing is that it's, right now, the way it stands, we can think of it as both ways. 3 circles to 2 stars, 2 stars to 3 circles. 3 rows of 3 circles to 2 rows of 3 circles, 2 rows of 3 stars to 3 rows of 3 circles. We can rearrange the image. We can have 3 rows of 2 stars and, 3 rows of 3 stars. We could do that, but it doesn't boil down the right way, right? If we're just comparing, if we compare 3 rows of 2 stars to 3 rows of 3 circles, that we could say that this is a 2 to 3 ratio. 2 stars in each row to 3 circles in each row. 2 stars to each row to 3 circles to each row. So it gets a little different to say. If you notice, the first way I was saying it was wrong. Well, it wasn't wrong. It just didn't make a lot of sense. 3 rows of 2 stars to 3 rows of 3 stars. Well, that's kind of confusing. But if we say instead that there are 2 stars in row 1 to 3 circles in row 1, that kind of makes a little bit more sense to me. But you can decide. Okay, I'm going to stop recording here. I think I'll do these in chunks. That's probably the best way. So this was the glossary entry, the introduction, reading the definitions. I will circle back to this really quick. Also, an ordered pair of numbers. This is what I was starting to talk about the explicit, how we need to do this more explicitly, I think, in mathematics, is helping you see ahead. Next year, 8th grade, algebra, and beyond, most mathematics is plotted on a plane for visual purposes. And we have double number lines that we're really used to from elementary school. Well, some of us might be. But we're moving into taking that double number line and taking one of those number lines and putting it perpendicular to the other. Rather than having 2 stacked number lines, we bring them up. So in this case, when we're dealing with ratios, there's this respect to 0 that they all must have in order for them to be sort of compatible, like a like term almost, being able to be compared. We want them to have that respect to 0, which is why we can use percents, because when ratios have this respect to 0, this connection at 0, the percents also have that connection at 0. So we can use percents to help us think about ratios. To compare 2 sets of numbers, so let's think about our stars and our circles, we might try to match elements in each set. So matching elements, this idea of grouping things, categorizing things, and matching them to compare. So we could think of this as 6 stars to 9 circles, but that reduces to 4 stars to 6 circles, or 2 stars to 3 circles. And with these images, it might help you to see where ratios become helpful in our world, because instead of having to think about 6 to 9 or 12 to 18, we can also think about 2 to 3, 4 to 6, and any other combination of those ratios. So that the fraction forms of these ratios would look like, let's do 9 circles to 6 stars, or 6 circles to 4 stars, or 3 circles to 2 stars. That's sort of in fraction form, and instead of fraction bars, we could have written colons. Now, why do we have these graphs? Well, I was talking about this double number line. So if we have a double number line, I just want to make sure I'm not writing in a reflection. Typically we say, okay, at 0 stars, well, what am I putting in the numerator? Let's put circles. So I have circles and stars. When I have 0 circles, I also have 0 stars. That's that respect to 0 component. When I have the most circles, let's say 18, or we can even go to 36, so we're playing with numbers beyond what's on the board already, so you can see the relationship between ratios. Say we have 36 circles total, how many stars must we have? Well, 36 divided by 9, right? If I took these 9 circles and multiplied them by 4, I would get this set up 4 more times. So that would give me my 36 circles. And then what is 6 times 4? Because I want to duplicate these together. They're linked. They're being compared. They're linked. So 6 times 4 is 24. So when I have 36 circles, I have 24 stars. Now we can cut that in half. 18 to 12. This is the cool thing with ratios that we don't get with fractions, is what I'm about to show you. Is that, well, let me cut it in half a couple more times. Let's get these on the board, and then I'll show you how it works. So we have 3 to 2, so let's cut this in half. I like cutting in half because it helps me visually. I can see halves of distances easier than I can see thirds. But now I have 9s and 3s, so I can't just cut in half. I have to use thirds. So we know that we can divide both of these by 3. So 9 divided by 3 would be 3. And 6 divided by 3 is 2. So I cut in half, and then I had to start dividing by 3. Now, where does this 6 to 4 come from? Where does the 6 to 4 come from, right? I couldn't get there by cutting in half or anything. But ratios are a multiplicative concept because we're multiplying, right? I'm taking these ratios and I'm comparing them with division. What is the best friend or the inverse? The mathematical inverse of multiplication is division. So if we're using quotients to make this relationship between numbers or sets of numbers, then we can also use multiplication to help us work around. Multiplication and division are inseparable in our number system. How can I create 6 fourths? We did it visually, okay, but this is where ratios are different than fractions. I can take this 9 to 6, and maybe I should zoom in here. I guess I can. I know how to do that. Look at me, always taking more time than I expected. Oh, maybe I can't zoom. Okay, I can't zoom. Anyway, let's try again. So I can take this 9 to 6, 9 circles to 6 stars, and I can just take away an equivalent ratio. I do not need common denominators. Ratios are different than fractions, but we can use fractions to help make sense of ratios. I hope this is coming out clear, and if not, I'll keep working on it. I can literally take away the 3 to 2 ratio. So I know that 9 to 6 is equivalent to 3 to 2. I know that these are equivalent fractions, right? 9 over 6 is the same as 3 over 2. But with ratios only, I don't need common denominators because these, we already said they're equivalent. These are equivalent fractions. So what would happen if we made a common denominator? Well, then I would get 9 to 6, and then when I subtract them, it would be 0, and that wouldn't make sense. But with ratios, I can take away equivalent ratios from equivalent ratios. It's like terms. It's taking two quantities and forming them into an object, a ratio, that combines these quantities. And then any other instance of combining those quantities, you can just add and take away from each other because they have the same units, right? The change of temperature over hours minus the change of temperature over hours to find the difference of the changes of temperatures from this year to last year. Okay, they have the same pair of units relating them in the ratio, and we can treat them like terms rather than like fractions, even though they look like fractions. Because with fractions, in order to add or subtract, we must get a common denominator. Okay. Because most of the time when we're adding and subtracting fractions, they're not equivalent. Well, they could be, but I would say that's a case. Okay. Back to this. 9 minus 3 is 6. 6 minus 2 is 4. Here we get our equivalent ratio. Okay? And this is also an equivalent fraction. But in ratio world, like with fractions, we tend to always want to simplify them down. With ratios, we don't need to. Sometimes we want to see what the ratio looks like at 36 or 18 or 9 or 6 or 4. Okay? Now, bringing this double number line up, remember, this is also relating to percents because from 0 to 100%, if we wanted to define 36 as the whole amount of circles that we're going to manipulate, then we can kind of stop there. But this 100% just represents the whole, and the 0% represents the lack of the whole. So in ratio thinking, it's really important to remember that 0 has this special property, okay, that 0% means complete lack of whatever you're measuring. And when you're using ratios, in order to be able to compare them, you want to make sure that they respect 0 in the same way. And the fact that if I can have no stars and I can have no circles. And when I have no stars, I have no circles. That's the most important part too, that they meet there. They have to meet at 0. So now let's bring these double number lines up into a two-dimensional plane so that you can get a vast introduction to what a ratio is before we start going through the actual task and using ratios. So let's plot 3, 2. 3 circles and 2 stars. Or 3 circles and 2 stars. 6 circles and 2 stars. 1, 2, 3, 4, 5, 6. I'm sorry, 6 and 4. So this becomes the 0.23. This becomes the 0.46. And then you can see, boom, here comes 2 more over to the right and 3 more up is 6, 9. And it will continue this way. And it creates a two-dimensional figure called a linear. Well, it doesn't create a linear function, but this line represents a linear function that is also proportional because it's based off of two quantities related by ratios that meet at 0, okay? FYI, this is 7th and 8th grade stuff, but you have it. I mean, it's right there. So I just want to make sure you see that it's connecting. I don't want you to have to wait a whole school year to realize this little jump you're going to have to take with ratios. Now, we can we can graph the exact same ratio relationship because there's no dependency. Like the stars don't depend on the circles don't depend on the stars. So we can write it both ways to maybe see the relationship a little differently. So instead of going over 2 and up 3 or up 2 and over 3, same thing, we're going to go, instead of going over 2 and up 3, we're going to go over 3 and up 2. Now, when you're counting on a graph, typically you do the rise first and then the run linearly, which is a little confusing because we're always ordering numbers on a graph with the x-axis first and then the y-axis. So we'll talk more about that later, but just bear with me. Hopefully you can follow still. So instead of going 2 over and 3 up, we're going 3 over and 2 up. So this got us to 3, 2. 3 heart circles, 2 stars. Same thing here. 3 circles, 2 stars. We just switched the axes. It's kind of like a reflection across a line. A 45-degree line. Okay. We need 3 more up, 2 more up. So then we're at 6, 4. And then 3 and 2 get to 9, 6. And then we get this line. So then the last step that you'll get to explore more in 7th and 8th grade is that we can now create an equation. So the number of circles is, and I guess I've been not filling them in. So the number of circles equals, so 9 equals the stars times what? What do we have to multiply the number of stars by to get the number of circles? What do I multiply 3 by to get 2? 3 times what makes 2? Well, I love the number 1 because, and I guess I can erase some of this here now. I'll erase the words because I'm sure you all aren't still reading them. So the question is, if we're forming an equation, I know I'm going off. You could have stopped the video by now because now I'm going off into 7th and 8th grade stuff. But you know me, I tend to do that. And I'm at 22 minutes. So that's ridiculous. Okay. Anyway. Circle equals what times the star. So what do I need to multiply the star values by to get the circle? Well, let's grab a ordered pair or a ratio and throw them in. So let's see. 9 circles to 6 stars. 9 equals what times 6? Well, this is confusing. I'm not really sure what times 6 makes 9, but I know that I have a fact family, like an equation fact family. So I know that from here, I have 4 other equations I can write. I can do 9 equals 6 times what? I can also do what equals, and then, where did the 9 and the 6 go? Well, if I cover up the 6, 9 equals that. But, okay, I'm multiplying the mystery number by 6. So that's the same as dividing the opposite. 9 by 6. Okay? There's another way I can write it, but it would not be helpful. So I'm just going to rewrite this one as. The third way to write it would be like this. 1 over something equals 6 over 9, which I don't think is very helpful, but I wrote it there in case anybody was curious. It might be helpful later because you're going to have to start practicing with proportions in 7th grade, but for now, let's just hold off. So what is this mystery number? I need to multiply this by something to get it bigger, but not as much as double. So double this is 12. So if this were a 2, then this should be a 12. It's not. If this were a 1, it would be a 6. It's not. It's halfway between. It's 1.5. 1 whole 6, and then half of a 6 makes 9. So I can also write 1.5 as 3 halves, right? Or you might see it as 1.5, or 1.50, or as a percent, it's 150%.